Okay. Thank you for coming. Let me start the section for 190p, the first section of the quarter. So let me introduce myself first. My name is Hyuk-Jung Kim. And you can just call me Jung. And then these slides or section materials will be uploaded on Canvas. So if you go to the Files tab, there's a folder called Discussion. So you'll see all of my slides there. So I'll also try to put my annotated version. So all of these things that I do during the sections on Canvas as well. And then I'm studying behavioral economics under the guidance of Anuji Chakraborty. So he's also the professor of this course. So so I'm really excited to be the TA of this course, because this is really related to what I do every day, what I study every day. Okay, so for each section, I'll try to make some questions. So sometimes I'll just merely change the numbers in the homework. Most of the time, or sometimes I'll try to make questions of my own, put some step-by-step guidance how to solve the questions. So what we will do during the sections will be mostly related to the homework questions every week. Any questions? Yes. So you can see that the PDF file for this week's section material is also uploaded on Canvas. Okay, so let me begin. So first question, reduction of compound lotteries. So I'm sure that you guys all know how to do this, but let me just give you a brief review of this one. So suppose that L, let me skip this question, because today we have lots of questions to cover. In the previous section, I couldn't complete all of the questions. So for this one, I'll put the answer key on Canvas. Second question. So this one is using actual numbers. Sometimes it is really helpful to go through questions with actual numbers. So if you see a questions like this, mix two lotteries, L1 and L2. So L1 and L2. Then these are my recommended steps. So in this question, I have first lottery where I have outcome 5, and then the attached probability is 0.2. For the second outcome, 3, the probability that 3 is realized is 0.8. So in the same way, we have second lottery, L2. So how many different outcomes do we have? 5, 3, and 1, 3, 5, 1. So we have 3 different outcomes. Okay, so after knowing this, now we can get a reduced lottery, alpha L1 plus 1 minus alpha L2. So I would put 3 different outcomes first, 5, 3, make some space here, 1. Okay. And then for each of these outcomes, let us calculate the corresponding probabilities. So for outcome 5, it is present in both lotteries. Okay, and then alpha is the probability that L1 is realized, multiply 0.2, which is the probability that 5 is realized within L1, plus 1 minus alpha times 0.6. Now for second outcome, 3, it is also present in both lotteries. So it is alpha times 0.8. So this is the probability that 3 is coming up from first lottery L1 plus 1 minus alpha times 0.2. And for the last outcome 1, this is only appearing in second lottery L2. So so we need 1 minus alpha here. Oops, I'm sorry. Okay, yeah. 1 minus alpha times 0.2. Okay. So if we calculate this, then we will have this final nice reduced lottery. Any questions? Okay. So and then last step, I would recommend checking if the numbers make sense. So you can check if all of these red guys, all of these probabilities are adding up to 1. Okay. If not, then you did something wrong. So let us check. Alpha times 0.2 plus 1 minus alpha 0.6 plus alpha times 0.8 plus 1 minus alpha 0.2 plus alpha, no alpha here, 1 minus alpha 0 times 0.2. Okay. Adding up, we have, if I add these two red boxes, I have alpha times 1. If I compute the remaining, they adds up to 1 minus alpha. Alpha plus 1 minus alpha is 1. So yes, they all add up to 1. So if this happened, then yeah, your answer is making sense. Any questions? Okay, so this was a warm-up question for today. One of the key concepts we learned in the class is the independence axiom. So let us do it. And then after that, we will go through rank-dependent utility, which is what we learned today. So independence axiom. So to understand the independence axiom, I came up with this question. We have two lotteries, L1 and L2. And then what does independence axiom imply if L1 and L2 are indifferent? So what does it imply? What is independence axiom? Sounds like my choice is independent to something. So if L1 is preferred to L2, then it implies alpha L1 plus 1 minus alpha. Suppose I come up with a third lottery, which can be equal to L1 and L2. L1 and L2. So if I come up with a third lottery, L3, then if I mix that with L1 and L2, with the same proportions, alpha, then if I preferred L1 over L2, then I still prefer mixture with L1 to mixture with L2. Okay, so mixing third lottery doesn't change my preference ordering. Okay, it is preserved in this way. Any questions? Alternative form, exactly equal. Theory says that if L1, so this is another way of stating independence axiom. If L1 is preferred to, if L1 is indifferent to L2, then alpha L1 plus 1 minus alpha L3 is indifferent to alpha L2 plus 1 minus alpha L3. So this another form of independence axiom is sometimes neglected, but this is what we need in this question, and maybe in your homework, I guess. So any questions? Okay. So second question. Okay, so I realized that this question is difficult without a hint. Here goes the hint. L3 is a combination of L1 and L2. Now let me read the question. So the agent will satisfy L1 indifferent to L2, indifferent to L3, where L3 looks like this. We need to find X and Y in here. So let us do that. So using the hint, let us get L3. Alpha L1 plus 1 minus alpha L2. So let us get the resulting compound lottery using the reduction of compound lotteries. So we have 3 different outcomes, 2, 5, and 1. So let me write them here. 1. Maybe I need a large space. 2, 5. Okay, so let us calculate the probabilities. So the question says that this is 0.14. Then this should be coming from this calculation. Alpha times, let me write in color blue. Alpha times 1 is here. Okay, and $1 is not in L1, so it should be coming from L2. So the probability that 1 appear is 1 minus alpha times 0.2, and this equals to 0.14, which is given in the question. Moving on, the probability of $2 coming up is alpha times 0.2 plus 1 minus alpha, the end. So $2 is not in this L2. Okay, so in here there's no $2. The last one is alpha times 0.8 plus 1 minus alpha 0.8, which is 0.8. So this number is fixed, 0.8. Okay, so yeah, so if we know what alpha is from here, then we can substitute alpha in here, and then we'll get the answer. Okay, so let's do that. So 1 minus alpha times 0.2 is 0.14. So 1 minus alpha should be 0.7. So alpha is 0.3. Which means that this guy is 0.3 times 0.2, which is 0.06. Okay. So this one was X, this one was Y. You got the answer. Why? And then why does this imply that L3 is indifferent to L1 and L2? It's because the final step maybe. So after calculating X and Y, now if L3 is a result of mixing L1 and L2, by the independence axiom, this is indifferent to L2 plus 1 minus alpha L2. So it's like fixing L1 and L2 and then mixing with a third lottery, which is L2. Okay, so if L1 and L2 are indifferent, then this kind of mixing should be also indifferent to each other. Okay, so this is coming from independence axiom, and this is just L2. So we can see that L3 is indifferent to L2. Any questions? Could you just add 0.8 and 0.14? Very clever. Very good. Very good. Yes, yes. So what Joseph said was that I don't need to calculate this guy here, because if I know this is 0.8 and this is 0.14, then the last number should be automatically 0.06. Very good. This is not what I intended when I was making this question, but I should admit, yeah, very nice way of solving this question. Very easy. Yeah, very good, very good. Yeah. So what you said is, works. Any other questions? Okay. So in the same way, we can solve the third question. Let me skip this for now. So we can also solve in a similar way. So this is almost identical question. So let me skip this one. So hint for this question also applies to here. So I'll post the answer key on Canvas. Okay, so the last topic for today is rank-dependent utility. I have two different questions here and here. So let's move on. Yeah, so this is what we learned today, right? Okay. So find the rank-dependent utility of a lottery under these two assumptions. Here. Okay. So first step. So when I solve this question, the name of this theory has rank-dependent utility. It has rank in here. So step one, I think natural step one is ranking the outcomes, because it's rank-dependent utility. Using common sense, we can say that $50 is the best, $30 comes next, and $10 comes at the last, the worst outcome. Okay. And then if you know how many outcomes we should consider, then maybe you can make tables like this to compute the rank-dependent utility. So what we need is two parts. Utility, sometimes we call this as a Bernoulli index. Maybe you learned this in 100 P or C. Okay, so this is utility for each outcome, each sure outcome. And then we need to, and then for this rank-dependent utility, so you're looking at this for the first time. So this is the adjusted probability in this RDU. Okay. So we're not just attaching a probability in here. We're doing something different in this rank-dependent utility. Okay. Any questions before I move on? So how do you do that? How do you calculate rank-dependent utility? We do it this way. So for the first one, so start from the best one. We have G. Now, what is the probability of having an outcome that is weakly better than $50? There is only one such outcome, $50 itself. And the probability of getting $50 is 40%, 0.4. So I put this one here. Let me make it smaller to make some space. Minus. Now, what's the probability of getting an outcome that is strictly better than $50? There's nothing, 0. And then what do you do from here? You use this weighting function here, okay? So GP is P squared. So G of 0.4 is 0.4 squared minus 0 squared, which is 0.16. This one, the second column, is just square root of 50. Any questions? So you just do this. Yeah, so we just continue what we did from above. Now, for the second outcome, $30, what is the probability of getting an outcome that is weakly better than $30? Is 0.4 coming from $50 plus 0.2, which is $30 itself. Okay, so that's 0.6 minus probability that we get an outcome that is strictly better than $30, which is 0.4. Where is this coming from? It's coming from $50 because $50 is strictly better than $30. And this is 0.6 squared minus 0.4 squared, just 0. Just to make sure, let me look at what I calculated before. This is 0.2. Yes, it is. And then utility of getting $30 is square root of 30. And then last one. Now $10 is the worst one in here. So the probability of getting an outcome that is weakly better than $10 is 100%. 0.4 plus 0.2 plus 0.4 is 1 minus G of, now there are two outcomes, 50 and 30, that is strictly better than 10. So we have 0.4 plus 0.2. This is G of 1 minus G of 0.6, which is 1 squared minus 0.6 squared, which is 0.64. And then the utility of getting 10 is square root of 10. Any questions? Okay. Now, does the probabilities in the second column add up to 1? Why or why not? Could you find the condition that make it happen? Do you think it add up to 1? So this number, and this number. Joseph said yes. Very good, very good. It adds up to 1. Okay. So why or why not? If we observe the numbers at the left here, can you see why? We can see 0.4, G of 0.4 is canceled out with this one. G of 0.4 plus 0.2 is canceled out with this one, right? So if I add up all of the guys here, then I will ultimately have G of 1 here, G of 0 here. So this is what I get if I add up all of the adjusted probabilities in the rank-dependent utility. So if G of 1 is 1, G of 0 is 0, then I get G of 1 minus G of 0 equals to 1. And then I will nicely have all of the adjusted probabilities adding up to 1. So when the professor was making this kind of question, so I copied this weighting function from the homework. So when we have, so weighting functions like this has a very good property, which is G of 1. If you just substitute 1 here, is 1. G of 0, 0 squared is 0. So if you satisfy this property, then adding up all of numbers here will give you 1, as we can see in the expected utility theory. Any questions? So this is the answer. We need these two conditions. Okay, so step 4, final one. So step 3 is actually not yeah. So this one should be an independent question. Yeah, it's not really a question. Step 4. So step 4 is the actual step 3. Anyway, calculate the rank-dependent utility. Similar to expected utility theory, we just multiply 0.16, the adjusted one, times square root of 50 plus. I was reading these pink numbers here and here. And then 0.2 times square root of 30. So outcome times the corresponding probabilities, 0.64 times square root of 10. I didn't calculate this before the sections, but you can do it with your Excel or a calculator. If we were doing something different, so suppose that if we were approaching this question using expected utility theory, this is RDA, then how do you calculate the expected utility? We will have square root of 50, square root of 30, square root of 10. So 3 different outcomes. And then we will just multiply the probabilities, right? So probability of having $50 is 40%, 0.4. This is 0.2. What was this? 0.4. Do you see what is happening here? The weight too thin. Weight for the good outcome, okay, has I'm sorry, this arrow, okay. So this one at the right, we have the expected utility theory. At the left, we have rank dependent utility. The weight for the good outcome has decreased, okay? And the weight for the bad outcome has increased. So it is adjusting so based on the ranking, it is adjusting the probabilities, and then maybe some of the outcomes that is good can be penalized, especially when you use the rating function like GP equals to P squared, a convex function. But I think this is going over the scope of this course. But good to know. Any questions? Okay. So this is one property of rank dependent utility. What kind of G function, rating function you use can affect the choices. Oh, I have 23 minutes left. Very good. Before moving on, I think this is the first and the last time I make an experiment in this course. So I made a very silly experiment that is related to what we learned in the class, also related to this question. So let's solve that. So let's do that one first. So if you go to this following link that I will share in the chatting room, then you can access, then you'll see 5 questions. 5 questions asking about your preference. So yeah, this one. So so for each of the questions, okay, so I didn't explain anything. So you just pick which one you prefer. So if you prefer the first option says that I get $10 for sure. I'm sorry, I get $10 with 50% of chance, and then I get 0 by 50% of chance. In the second option here, then you will get $5 for sure. If you're indifferent, you can choose this one. So after choosing all of these, like this, you can go to the final button. You can click the submit response button, and then see the result. So if you're done, I can check if you're done. Let me give you 2 minutes, and then we will see the result. Oh, okay, so we are all done. Very good. So let's go to the result. Let me just manually put thank you here. Okay. Okay, so there were 4 participants, so 2 coming from the previous section, and also there are only 2 people here. So, so we counted the number of violations of independent axioms in here. So how do we do that? So I was first giving you a choice like this. Let me share my screen using my computer. Okay, yeah, so I was first asking you to make a choice like this. Okay, make a choice between 1 and 2. 1 and 2. Okay, and then suppose that you are you preferred, so you selected this one, the first one. Okay, then what happened? Then using the dependence axiom, I can mix with third lottery, which is this one and this one. Okay, and then if you suppose that you have chosen this one, then you are breaking the independence axiom. Nothing wrong to violate independence axiom. So I also violate independence axiom. So it's not something that we should keep. Okay, but if you just talk about the axiom, if you reverse your choice, then you are violating independence axiom. So for question 2, what I was doing is that I was using alpha equals to, what did I use? So for example, question 2, I was using alpha equals to 0.2, okay? And then L3 of my choice was 5, 0.2, so $5, 0.2. You get nothing for 80%. So I was mixing with this. In this way, I was making 4 other questions, and they compare your choices between question 1, question 2, question 1 versus question 3. Question, where's the thank you page? Question 1 versus question 4, question 1 versus question 5. Okay. So if you switch your choices, then I counted that as violations of independence axioms. So out of four participants today, we had only 1 violation of independence axiom. Okay. Any questions? You will see similar questions in the exam or homework. So let's move on to the actual question for today. So let me share my screen using, there's something in the chat room. Okay. Yeah, let me share my screen using my iPad. To go back to the question. Yes. So question 3b. Suppose that an agent is indifferent between these 2 options. So similar to what we did before. Okay. Assume u of x is x. I said blah, blah, blah in this here, but let's ignore. And then when calculating the rank dependent utility, we use this weighting function. Okay. Under dependence axiom, check that the agent is indifferent between L1, L2, L3, where L3 equals to alpha L1 plus a typo, 1 minus alpha L2. And then L3 can be these 3 guys, depending on my choice of alpha. Okay. So for example, L3 alpha 0.5 is 0.5 L1 plus 0.5 L2. So there's actually no question in here in this sub question 1. Yeah. You need to check. It should be correct because I did it myself. And then, do you feel the same? I leave the answer for you. So do you really think that this lottery is indifferent to L1 and this lottery is indifferent to L2? So if you say yes, then you're more closer to expected utility guys. If not, then you are more closer to behavior ideas like rank dependent utility. Nothing right or wrong. So let me skip the first question. We don't need to solve anything. Question 2, fill the following 3 tables. Okay, so in the first table A here, this one, A, I was putting the third lottery where I was using alpha equals to 0.5. Second table, I think I used 0.9. Not completely sure. And then in here, I think I was using 0.1. Okay. So if you do it, then so this 0.25 is coming from here, 0.5 coming from here, 0.25 coming from here, like this. Okay. Okay, yeah, so it's all correct. So using this, what you need to do is just calculate the adjusted probabilities for each outcome. So let me do the first one. Table A. For $16, probability of getting something weakly better than 16 is the probability itself, because $16 is the best one, minus G of 0. And for the next one, $8, there are 2 outcomes, 16 and 8. That is weakly better than 8. So we have G of 0.75 minus G of this one. So we need to pick the one that is strictly better than 8. But if you solve this question 100 times, then you realize that this number is just copy and pasted from here. So you need 0.25 without too much thinking. And then here, the last one is automatically G of 1 because this is the worst one, minus copy and paste of this one. I was going step by step last time because we're doing this for the first time maybe. Here, we can speed up. And then, now this one, we need calculator. I did solve this question before coming to the sections. Let's see. This is 0.625. This is 0.5. This is 0.4375. Okay. Okay, yeah. And then in the same way, you can calculate. So let me do one more. The table B. And here we need G of 0.45 because 16 is the best one. So there is only one outcome that is weakly better than 16. 16 itself minus G of 0. And then for this one, we add these 2 outcomes, 0.55 minus G of 0.45. For the last one, we have G of 1 minus G of 0.55. Calculating this, I have 0.2025, 0.1 in here, 0.6975. Okay. Any questions? In the same way, I have 0.0025, 0.9, 0.0975. Okay. Oh, what is G? So G is a weighting function. So G is a weighting function. in the rank dependent utility. So this is used to rank. So this is used to rank different outcomes and then adjust the probabilities for each outcome. And then we can see that after doing all of these things, utility value in table B is the smallest, while utility value in table C is the largest, if you believe my calculation. So could you provide intuition behind the result? Why do we have such result? So let's try to interpret the result. So, so from the beginning of the question, we saw that all of these three guys are indifferent to each other. If you believe independence axiom, and then if you are a risk neutral person. However, if we go to rank dependent utility, we can have different answers. It depends on the shape of the G function, the weighting function. We had G equals to P squared as our weighting function, G of P. So if we plot this function, G of P at the y-axis, and P at the x-axis, the domain, this is 45 degrees line, then G of P looks like this, where this one is 1. 1, 0. So G of 0 is 0, G of 1 is 1. Now G function looks like this. So at the very starting point, okay, so this is the region when we calculate the good outcomes. Okay, so for example, for B, we had 0.5, P of 0. I'm sorry, G of 0.5 minus G of 0. So I was subtracting this point A. So yeah, so I was computing the difference between A and A prime. Okay, but if you were using expected utility theory, what would you do? You are computing the difference between here and here. So the good outcomes are underrated. So good outcomes underrated. Now, if the value for the good outcome was high, it is even more penalized. Okay, so if you have 0.05, then there's not much difference between expected utility and rank dependent utility. But if we go to here, the gap between expected utility and rank dependent utility increases. Okay, so if you have high probability for good outcome, you get penalized even more under our rank dependent utility. That's what is driving the difference between B and C. Okay. Yeah, but it was based on our assumption of this G function. If you have a convex function, convex G function like this, then we have this result. If you have another type of G function, maybe it can be inverted like this, and we will have a different result. So choice of G is very important. I think this part is maybe going beyond what we learned in the class, but it's good to know all the steps to compute rank dependent utility. Important for your homework, maybe important for your exam. Okay, so we have 6 minutes left. This is the first section, so let me end early for today. So thank you guys for coming. See you guys next week. Stop recording.